So in this lecture we talk about examples of spec. So we have already talked about spec before. Spec is nothing but prime ideals of a ring. So the first example is spec of K, where K is any field. So this will have only one point, which is 0. Spec of Z, it has a point which is 0, and it also has closed points P of Z, where P is prime. So closed points correspond precisely to the prime ideals which are also maximal. So if the ideal is maximal, we have closed point. So 0 is not maximal, so this is not closed. In spec Cx, where C is complex, we have a point 0, and the closed points are of the form x minus alpha, where alpha is a complex number. Spec of Rx, this R is real. Again, it has point 0. The closed points are of the form x minus beta. Beta is a real number. But here we have these irreducible polynomials of degree 2. So these are polynomials in Rx. Now we can talk about spec of Kx, where K is any field. This is a point 0, and closed points are irreducible polynomials in K of x. We generally take these irreducible polynomials to be monic. Now we talk about spec Zx. Z is integers, so points are 0, and other points of the space are Pz, where P is a prime number, just like here. So we are copying 0 and Pz from here, and then you have F, which is irreducible. We obviously take F to be monic, and here F could have any positive degree. So notice for Rx, your maximum degree was 2. So either you have degree 1 here, linear factors like this, or you have degree 2. Here it could be any positive degree, and the closed points are generated by both this prime ideal and F. So it has to contain these two. So this is not closed and this is not closed. This is the only maximal ideal. So again, P is prime, F is irreducible monic polynomial which could have any degree. Now we come to a very important fact. So say we are given a ring homomorphism phi from A to B. This will induce a map spec of phi from spec B to spec A. So this is contravariant map. So we will write spec of phi as just psi. Now this psi is actually a homeomorphism from spec B to prime ideals of spec A, and precisely those prime ideals which contain the kernel phi. So that is prime ideals in spec A which will contain the kernel of phi. So anything which gets mapped to 0 should be contained in the prime ideals here for a homeomorphism from spec B to spec A. So this is important, and this we are going to refer to again and again. So our very first important example about which we have discussed in localization is, say we are given a morphism from A to S inverse of A. So this S inverse is a multiplicatively closed set. So this ring is nothing but localized with respect to this multiplicatively closed set S. So this will give rise to a homeomorphism. You have contravariance, spec of S inverse A to spec of A. And we have seen what are the prime ideals in here. So this we have seen in localization. So prime ideals in S inverse A correspond to precisely those prime ideals in spec A. So those prime ideals in spec A such that this prime ideal, you intersect it with the multiplicatively closed set, is just the null set. So this is important property of localization. So this we need to remember. And we have talked about this in our lecture on localization also. So another important example. So say we have this natural map from integers to Zx. Now this will induce this map psi from spec of Zx to spec Z. So you notice that arrow has been reversed. So notice what are the prime ideals of spec Z. They are precisely 0 and P of Z. So they are 0 and Pz for P prime. So you're taking union over all primes. So spec of Zx is just psi inverse of 0. Your point 0 is also the generic point because closure of 0 will give you the entire space spec Z, and then phi inverse of these points P of Z, and you have to take over all primes. So let us describe this space starting with psi inverse of 0. So we say that this prime ideal of spec of z of x, this lie is in psi inverse of 0 if and only if this prime ideal intersecting with integers is 0, because kernel is just 0, so it contains kernel. So and it contains only the kernel consists of only 0, so this p intersect with z is 0. But we can construct a multiplicatively closed set S which does not contain 0, so you have z minus 0. So we can rewrite this statement by just dropping 0 from here to the following conditions, that p intersection S, where S is multiplicatively closed set, which is z without 0, this is null set because you just taken 0 out. So now this looks exactly like this. So p intersection x is null set, and this corresponds precisely to ideals in S inverse of A. So we have S inverse of z, and you know S inverse of z is nothing but our rationals, and you take x as such here. So we have a homeomorphism corresponding to this first thing. Psi inverse of g, you have homeomorphism to spec of qx just from this map here. Now we come to the second part. So you have to do this over all primes. We just do it over one prime. So say we are given a prime number in integers. Then this prime in spec zx lies in the inverse image if and only if this prime lies in our prime ideal here. Now you can see this from here because spec of zx, so this prime should either be contained in this pz or it should be contained here. So this has to be the case. But on the other hand, you can only talk about we are saying that spec p, there is a homeomorphism if spec a contains kernel of phi, so it has to form the kernel. So this p is getting mapped to some kernel here. So for it to get mapped to kernel here, you have to have this map of this form z x over p. So only then this p would lie in the kernel. So notice we are using two things here. First, we are using the property of spec of zx because it inherits the prime ideals from z of this form, and the second, we are using this kernel of phi which is forcing for this map. So this gives us, so z modulo out with the prime ideal p, you get fpx because this x comes here, and z modulo p will give you fp. So again you have a homeomorphism like this from psi inverse pz to spec of fp of x. So now we will come to a very visual picture of Mumford which describes spec of zx and this morphism visually. So this picture we have taken from Mumford's Red Book, and this is in section 2.1. So this, you can think of this entire picture here is say spec of zx. So this top part is spec of zx, and here we can think of it as spec of z. So say 0 is here, and this is prime ideal 2, prime ideal 3, 5, 7, and so on. Now 0 is the generic point because if you take closure of 0, you get the entire space both here and here. So this line here you can consider as our f2x. So again we talked about this, our prime ideals in zx, they consist of this prime p, and this point x corresponds to this irreducible polynomial. So this is irreducible in zx. So point this is prime p and irreducible polynomial f. So similarly this 3 is prime and irreducible polynomial is f. 5 is prime and irreducible polynomial is f, which is x. So correspondingly here you can again say it is 7 comma x, and so on. Now we can talk about our irreducible polynomial x square plus 1. So this is again irreducible in zx, but its behavior changes right here in f2, because here you notice that this x plus 1 square is x square plus 1 plus 2x, and this is 0 in f2x. So this x square plus 1 actually splits as x plus 1 square. So you can write it as 2 comma x plus 1. There is a tangent line showing the multiplicity is 2. So here nothing is happening, but here again you can see this line as f5 x, and you can see this multiply these two, x plus 3 times x plus 2, and you get let me write down right here, x square, and if you multiply this you get 5x plus 6. Now you're working in f5x. This will become 0 because this is 5. This 6 will become 1 modulo 5. So again you get x square plus 1, but this x square plus 1 is split into now two factors, 5x plus 2 and 5x plus 3, and that's precisely why it is going like this and it is splitting like this in two different parts. Again, if you just focus on this line, you have this prime ideal 2, but notice that this is not maximal, so closure of this prime ideal will actually give you the entire line. So it is a generic point, it is not a closed point. This is a closed point. This is also a closed point, and as we said, this prime p, this is not closed. Similarly, 3 here is not closed. So another ideal here is of the form p comma f. This x plus 2 is irreducible, p is prime, this is closed. Here you have x plus 4, 5. This is again we know that it is irreducible. This is prime. Now this is not maximal. This is again a generic point. Take its closure, you get the entire space. Similarly, this corresponds to 7, and so on. So we have discussed this map here. So only thing remaining is 0. So we put 0 here. So we should have our qx right here. But q is a field. So again, you can talk about irreducible polynomials here, and point 0. So this says 0 generic point, you can say is in here. But anyway, this point is everywhere. This is the generic point. So this is the description of the picture in Mumford.